Welcome back, guys. Today we're going to be taking a look at topic 7.3, graphing absolute value functions. Now, we've already looked at how to graph absolute value functions for linears. Today we're going to go one step further, and we're going to look at graphing absolute value functions for quadratic functions. So before we go into our examples, we're just going to do a quick review of our absolute value function definition. So an absolute value function can be defined as any function in the form y equals a times the absolute value of b times x minus c plus d. And a, b, c, and d are all any real numbers, and a cannot be 0. Now again, the basic example that we started with is y equals the absolute value of x. And it's important to note that y equals absolute value x is a piecewise function. So in other words, we have to consider different sections of the graph. If x is positive for the absolute value of x, if we have x, x can be greater than or equal to 0. If we have negative x, then x is less than 0. And again, we're going to get into piecewise functions a little bit more in another lesson. All right, so let's take a look at our first example here. So just like in our last lesson, when we were looking at linear functions and we were taking the absolute value of a linear function, we had two different ways that we could determine that absolute value. One was to use a table of values. The other was to use the graph itself, and the idea that when we take the absolute value of a number, if anything is positive, it stays positive. If anything is negative, it becomes positive. So we're going to graph the function y equals x squared minus 4. We're going to start off by listing some tables of values here. So we're going to start with 0, plus or minus 1, plus or minus 2, and plus or minus 3. Now this is basically a shorthand way of writing our table of values, and that's because we have x squared. So it doesn't matter whether x is positive 1 or negative 1. When we square it, we're going to have the same y value. So filling in the table of values, we have 0 squared minus 4 becomes 0 minus 4 is negative 4. Plus or minus 1 squared minus 4 becomes negative 3. So 1 squared minus 4 is negative 3. Plus or minus 2 squared, either way we're going to get 4. 4 minus 4 is 0. And then we have plus or minus 3 squared minus 4 equals 5. Now, in all cases, when we look at this and we were to graph this out, based on the fact that this is a y equals x squared minus 4 equation, we know that this is going to look like a parabola. And in this case, we're taking the absolute value. This graph will be an absolute value graph. All right, so let's take a look at what happens to our y values when we take the absolute value. We have a negative 4 becomes 4, negative 3 becomes 3, and then we have 0 and positive 5. So we're going to start off by graphing our original function. We have 0 and negative 4. We have positive 1 and negative 3. We have negative 1 and negative 3. Positive 2 and 0. Negative 2 and 0. And then for positive 3, we have 5. And negative 3, we have 5. All right, so we start off by sketching that graph, coming down through those points. And continuing on. All right, now taking a look at the absolute value, we have 0 and 4, and then we have plus or minus 1. Plus or minus 1 gives me 3, and 3, and we have 0 and 0, and then we come up to 5 and 5. So as we sketch this graph, what's happening is the graph comes down all the way to that y-intercept, then it pops up, comes down, and then pops back up here. So notice the only thing that's changed is that any values that were in the negative y's have now become positive. So now we have sort of this shape, almost like a W. Okay, so anything that was negative has popped up. All right, so let's take a look at our domain and range for the function and the absolute value of the function. So for the domain of our original function, we have a graph that looks like this. And we have our equation is y equals x squared minus 4. Our domain for that function is x is the element of reals. And our range for that function is y is greater than or equal to -4, and y is the element of reals. Now taking a look at our absolute value function, we have y equals the absolute value of x squared minus 4. Again, our graph had that W shape. Our domain is still element of reals. X is the element of reals. And our range. Notice now everything is flipped up. So we have y is greater than or equal to 0, and y is the element of reals. So with our original function, we had a minimum, an absolute minimum at y is greater than or equal to -4. With the absolute value function, that minimum has now flipped up, and we have what's called a local maximum. All right, now the question is, what is the effect of the vertex of the original function when the absolute value is taken? So essentially what's happened is we've reflected that vertex in the x-axis. So our original point, we had a vertex of 0, -4, and now that's become a new vertex at 0 and +4. Now, taking a look at another example here, we can also figure out what the absolute value of our function looks like by using the graph itself. So we're going to start off again with our original function. Our original function would be y equals x squared minus 3x minus 4, or we could write that as f of x. And if we want to graph our original function, the first thing we're going to have to do is find our zeros. And luckily, in this case, this graph is easily factorable. So we have 0 equals x squared minus 3x minus 4. When we graph, or when we factor that, we have x minus 4 and x plus 1. And that gives us x equals 4 and x equals -1. Now looking for our y-intercept, we would have y equals 0 squared minus 3 times 0 minus 4. We substitute, or we calculate those out, and we have y equals -4. All right, now for our vertex, we could graph this on our calculator and find our vertex. It would be 1.5 and -6.25. Now another way to find my vertex is to complete the square. So I'm going to have y equals x squared minus 3x minus 4. And that gives me x squared minus 3x plus, remember, half squared, so 9/4 minus 9/4, all minus 4. When we factor, we have x minus 3/2 squared minus 25/4. Now, leaving this as a fraction, we would have 3/2 and -25/4. If we wanted to turn those into decimals, that's where we would have our 1.5 and -6.25. All right, so using that information, we're going to plot our original graph. So we have zeros at 4 and 1, or 4 and -1. We have a y-intercept at -4, and we have a minimum at 1.5 and -6.25. All right, and then we sketch our graph. Okay. If you wanted more detail, you could use your table of values to find more points on there. And then we want to take our absolute value function. Now, when we're doing the absolute value, what we're doing is we're reflecting in the x-axis any part of the original graph that's below the x-axis. So this piece down here is below the x-axis, so that part's going to get reflected. And so where we had our vertex of 1.5 and -6.25, we're now going to have a local max at 1.5 and +6.25. Our zeros have now become our invariant points, and the graph is going to swoop down and swoop down, and then swoops up this way and swoops up this way. So essentially this piece down here disappears. All right, so let's take a look at some more examples here. Again, we're just using the graph that's given to us to determine our absolute value. So for the first function here, We have an original linear function. Notice we're not given the equation, so we're just using the graph to determine the absolute value. So anything that is below the x-axis is going to flip up. So this top part here is going to stay exactly as is, and then that piece below is going to flip up. So just to keep my graph straight here, I'm going to use a ruler or a straight edge. The first part of the graph just stays above, as it already is, and then the other part of the graph is going to flip up. So if it would help, I notice that this point here is going to be at 10 and negative 10. So I can put a point here and turn my ruler. And draw that part of the graph. So again, now that we have the absolute value drawn, this piece disappears. So you can just cross it out. Taking a look at the next graph here, we have this part of the graph is curving up. That part's going to stay up. And then the other part of the graph is going to curve up. So if we look, this point here is going towards 5 and negative 5. So it's now going to be at 5 and positive 5. And so that graph is just going to curve up in that direction, and this piece disappears. Now, it doesn't matter what types of graphs we throw at you, we're still just using that exact same idea over and over. At our x-intercepts, the graph is going to have invariant points. Any part that's above the graph is going to stay put, and then any of our other points are going to flip up. So this point here is at negative 3 and negative 6, so it's going to flip up to negative 3 and positive 6. This one here is at 3 and negative 6, it will become 3 and positive 6. So that graph's going to go up this way, and then this part here is going to connect this way. And again, we just eliminate those other pieces. Now, taking a look at our last graph here, again, we're looking at the pieces that flip up. So this point is up here. It's going to go across and then come down. And this part curves, stays curved. This piece here is now going to curve up and down. And this part stays put. And again, another piece that's curved up. And then this part stays as is. All right, so taking a look at how the points are affected. If a graph of y equals h of x passes through the point negative 2, negative 9, then the graph of y equals absolute value h of x must pass through the following point. Well, the negative 2 is going to stay negative 2. It's only the y value that changes. So that's going to become negative 2, comma, positive 9. And finally, we're going to take a look at a few more graphs here. These ones have been transformed, meaning they've been either shifted up or down, or they've been stretched in some way. And we're just going to look at how the domains and ranges are affected. So taking a look at the first one here, we have y equals the absolute value of x plus 3. Our domain is x is the element of reals. In fact, for all three of these graphs, x is the element of reals. Now we're assuming that there are arrows on the ends of these graphs. And the last one, x is the element of reals. Now taking a look at our range for this graph here, our graph is touching the x-axis, so y is greater than or equal to 0, and y is the element of reals. Here our graph's been shifted down too, so y is greater than or equal to negative 2, and y is the element of reals. And for this one, the graph has been reflected, but it's still touching the x-axis, but this time instead of y being greater than or equal to 0, it's less than or equal to 0, and y is the element of reals. Taking a look at our zeros, for the first function, our zeros are happening at negative 3, comma 0, and our y-intercept happens at 0, comma 3. For the next one, the zeros are happening at negative 2, comma 0 and 2, comma 0. So negative 2, comma 0 and 2, comma 0. And our y-intercept is happening at 0, negative 2. For the final graph here, we have just 1, 0 right at the origin, so 0, 0, and then our y-intercept is also 0, 0. All right, so if you notice, it doesn't really matter what kind of graphs we throw at you. That concept is the same over and over. We're just taking the values that are in the negatives or the negative y values, and we're flipping them up to the positives. We can get some pretty crazy looking graphs sometimes, but it's the exact same process over and over. Hopefully that gives you enough examples today. Have a great day, and we'll see you soon.